In the remainder of this chapter, we will be looking at phase changes, both from a qualitative or non-mathematical point of view, but also to look at the calculations that take place that deal with phase changes. Before we do that, though, we should make sure we define our different types of phase changes, because if you think about it, we could draw a chart as we add heat versus temperature. And so our compound might start out as a solid. Then when we reach the melting point, we continue to add heat to it, but the temperature stays constant. So during a phase change, for example here when we're going from solid to liquid, we have to add heat. So if you think about this, if this is water, for example, we can heat up ice until it gets to 0 degrees. At 0 degrees, it doesn't just instantly turn into water. We still have to provide more energy in order for it to overcome the separation or the phase change. It becomes a liquid, we can heat up the liquid, and then when we reach the boiling point, again, we'll have a constant temperature where we're still applying heat, and that's the temperature where it turns into a gas. So what are the names for each of our phase changes? So we can go from solid to liquid, which is melting, liquid to gas, or vaporization. And then of the three phase changes that require heat to be added, the one that we see least often, solid going directly to gas. And that's known as sublimation. What's the most common place where we see sublimation? Well, if you've ever worked with dry ice or solid carbon dioxide, that's an example of sublimation. Because you look at what happens, those pieces of dry ice, they don't become liquid carbon dioxide, they go directly from solid to gas. We also have the three phase changes that go the other direction. Gas to liquid, liquid to solid, and gas to solid. So gas to liquid, known as condensation. Liquid to solid is known as freezing, of course. And the unusual one, gas to solid, known as deposition. Now we have terms that we use to describe these situations. And so for any phase change, we can calculate the heat involved. And so the heat of a phase change is actually pretty easy to calculate. So we define that heat as Q. And that Q is equal to the delta H. This delta H value is specific to the substance and the type of phase change. So for water, for example, water has a delta H of vaporization. That's for it. That's for its evaporation. It has a delta H of fusion for melting, and a delta H for sublimation. Now you might be asking, why don't we have 6 of these delta H values? Well, the reason is, if you think about what's going on, condensation and vaporization are basically the opposite process. So there is a delta H for condensation, but it's just the vaporization delta H with the opposite sign. Same thing for freezing, and same thing for deposition. So these delta H, or what we call enthalpy, and that's something we'll talk about what that means later. All we have to do is multiply delta H times the amount. Now, what units does that amount need to be in? Well, it all depends on delta H. We sometimes find delta H as joules or kilojoules per mole, and sometimes we also find it as joules or kilojoules per gram. Doesn't matter which way we find it, just as long as the unit that we use for our amount is consistent with the units for delta H. So that's how we calculate the heat that's transferred during a phase change. What about heat calculations not during a phase change? So in other words, what if we have a liquid and we just heat it from 20 degrees to 50 degrees? How do we calculate that? In that case, Q is equal to M, which is the mass, times C. C is known as the specific heat of a substance. It's a constant for every substance, but it's dependent both on what the substance is and its phase. So in other words, is there a different specific heat for liquid water and solid water? The answer is yes. And then we multiply this by the change in temperature. This is one case where you can use your temperature in Celsius or Kelvin. It doesn't matter. Why doesn't it matter? Well, let's say we are changing the temperature of something from 10 degrees Celsius to 30 degrees Celsius. What would delta T be? Just 30 minus 10? Or 20 degrees Celsius. But let's say we had converted those to Kelvin. Then we have 283.15 Kelvin going to 303.15 Kelvin. What's the difference? Again, it's still 20 degrees. So because we're taking the difference here and not just looking at an absolute value, it doesn't matter for delta T whether we use Celsius or Kelvin. But these are the two equations that we use for calculating heat and amounts of heat that are transferred. And so now we'll do a couple of examples, and then you have some to practice. So we want to calculate the amount of heat that's needed to melt 36 grams of ice. And I've given you the delta H fusion for water. So remember, for a situation like this is a phase change. Q is equal to delta H times the amount. Now, given that our delta H value is in kilojoules per mole, then we'll want to use moles in this equation. But as we'll see in a moment, there's actually two ways we could do this problem, and we'll do it both ways. So here's the first way. We're going to take our 36 grams of ice and convert that to moles. Molar mass of water is 18 grams, and so we have 2 moles. So Q is equal to 6.01 kilojoules per mole times 2 moles gives us 12.02 kilojoules per mole. I'm sorry, 12.2 kilojoules. What's the other way we could have done this? Well, we could have taken our delta H value of 6.01 kilojoules per mole and converted this to grams. So 1 mole of water is 18 grams. And so we'd get 0.33 kilojoules per gram. And then if we took 0.33 kilojoules per gram times 36 grams, again, we get to 2 significant figures, 12 kilojoules. So we've done the same calculation in both cases, just really in a different order. Now let's do another problem that involves even more situations. So now we have 1 gram of ice, and we want to take this 1 gram of ice, which is starting at minus 20 degrees, and we want to get it up to 40 degrees. So initially this might seem like this is just a very simple problem. We're just going to heat it up by 60 degrees, so we take mass times C times delta T. What makes this more complicated is it turns out this is actually a 3-part problem. Because what's going to happen with the ice, we have ice here at minus 20. So we're going to heat it up, and then it's going to hit 0 degrees Celsius. What's going to happen at that point? Well, it needs to melt. And so it'll melt and stay at 0 degrees. Once it's fully melted, then it can be heated up to 40 degrees Celsius. But realistically, this is a 3-part problem that we're working on here. So we have to calculate 3 different Q values. And just for simplicity, we'll refer to them as Q1, Q2, and Q3. So Q1 is going to be heating the ice up to 0. Once we get Q1, Then we need to melt the ice. And this is constant temperature. After we've done that, then we heat the water. And this is going to go from 0 degrees Celsius to 40 degrees Celsius. So 3 separate calculations. None of these calculations are terribly difficult. It's just we need to remember to use the right constants and do all 3 of them. Finally, at the end, we'll calculate our total Q as the sum of each of the individual steps. Alright, so let's do each one of these. So first we're going to calculate Q1. Q1 is our heating of the ice from -20 to 0. So I know we originally said this equation is m times c times delta T, but notice in this case the values for C are in moles. That's not a problem. All we need to do is convert our 1 gram of water into moles. And we get 0.06 moles. Now, this is heating up solid water, so I need to use the specific heat for water when it's a solid. And then what's the change in temperature? Well, we've gone from -20 to 0, so that's 20 degrees Celsius. If we multiply those out, we get 361 joules. So let's jump down and fill that number in. So Q1 is 361 joules. Now we need to melt the ice. For melting ice, this is equal to the delta H value, and we get this from the previous problem, 6.01 kilojoules per mole. And we already calculated our number of moles in the previous step is 0.06 moles. And so that gives us a total of 41 joules. No, I'm sorry. I've got my numbers wrong. So let's get rid of all these numbers. I've got my calculations all set up correctly. I've just written down the wrong answers. So this first one actually gives us 41 joules. The second one, when we multiply it correctly, gives us 0.361 kilojoules. But knowing that the first one we did is already in joules, if we want to add these together, they're all going to have to be in the same unit. So we can multiply that, we get 361 joules. So that's our Q2. Finally, our Q3, we're going to calculate just like we did Q1. The only difference is because we're now heating liquid water as opposed to solid water. As we saw when the problem was originally written, we have a different value for our specific heat capacity. Now we have 75.3 instead of 36. Change in temperature here is 40 degrees, and we get 181 joules. So we add that one in here, and we can sum all of those up, and we get a total of 583 joules. Alright, so our final piece of this now, so we do have some practice that you can work on. But our last piece here is just a few other terms that we want to define. And these terms are what are known as supercooling and superheating. So what these are is these are situations where a molecule or a whole bunch of a molecule has gone past the phase change temperature without changing phases. Typically what this means is that maybe you've cooled the water down below 0 degrees, but the water molecules haven't organized themselves well enough to actually form a solid. And so typically at that point, you just have to slightly agitate the compound and the phase change will complete. Final piece here is to look at what's known as a phase diagram. And this relates pressure and temperature. And that's because the temperatures that phase changes happen at aren't necessarily constant. So does water always boil at 100 degrees Celsius? The answer is no. We know that for many, as we change altitude, the boiling point of water changes. And that's because the definition of boiling point is the point where the vapor pressure of a liquid is equal to atmospheric pressure. So when the pressure is much lower, such as at higher altitudes, that means the vapor pressure doesn't need to get as high and you don't need to heat the water as high. So at higher altitudes, you get lower boiling points. And so typically a phase diagram looks like this. And we have our regions. At either very low temperature or high pressure, we have solids. At either very high temperatures or extremely low pressures, we have gases. And then this intermediate region are where we find liquids. And then these lines that appear, those are where the phase changes could take place. Now, two important points to note. One is that you may notice there's a point where all of them intersect right here. This is known as the triple point. The triple point is where all three phases can coexist. For some compounds, it's something we might see pretty commonly, but for water, for example, it's not something we really see. Water's triple point is actually right around its normal freezing point, just slightly above 0 degrees Celsius, but only 4.58 torr. And if you recall, standard pressure is 760 torr. So that's one important point. The other interesting point is up here. These lines don't extend indefinitely. We end up here with what's known as the critical point. And above the critical point, compounds turn into what's known as a supercritical fluid. What is a supercritical fluid? It's basically a point above where distinct phases don't really exist. And so there's actually a lot of very interesting properties that we find for compounds at that point. But again, well beyond the scope of this course. So at this point, you should go to the next in-class exercise. I believe it's number 15, and you'll get some practice with some of these calculations involving heat transfers.